The following is our second conversation with Dr. Alex Carter, a cosmologist specializing in the origins of the universe and the nature of dark matter. Dr. Alex Carter is a renowned cosmologist from the University of Cambridge, recognized for his groundbreaking research on dark matter and cosmic origins. With a unique approach that merges indigenous astronomy with modern science, Dr. Carter inspires audiences to explore the universe's greatest mysteries. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Dr. Carter, thank you for joining us again on the Convincing AI podcast. How are you doing?
Thank you for having me. I'm doing great and excited to be here. How are you?
I'm doing great as well. So can we start again with just a quick review of your background and experience?
I'm Dr. Alex Carter, known for blending indigenous astronomical knowledge with modern cosmology. My groundbreaking research focuses on cosmic inflation and mapping the early universe. I've been honored with the Breakthrough Prize in Fundamental Physics. It's a pleasure to share insights and make complex ideas accessible.
Okay, and I know we covered a lot last time, but I'd like to take this one step deeper. Is that okay?
Absolutely. I'd be delighted to go deeper. What specific area would you like to explore further?
Given the discussions about the possibility of our universe existing inside a black hole and the parallels between their densities, can you elaborate on how the transition from a black hole singularity to an expanding universe might actually occur? And what specific physics might govern that transformation?
The idea that our universe might exist inside a black hole is a fascinating one. Essentially, it suggests that the singularity at a black hole center could be analogous to the Big Bang singularity. If this were the case, the transition from a black hole singularity to an expanding universe could involve extremely dense and energetic states governed by quantum gravity. This is an area where classical physics breaks down, so theories like loop quantum gravity or string theory could potentially describe this transition. The specific physics might involve a bounce or phase transition, where instead of a singularity, there's a smooth transformation that allows for the expansion we observe as our universe.
So one point of confusion is if we have a sufficient amount of matter in a small enough density, we have a black hole. Is that correct?
Yes, that's correct. A black hole forms when a sufficient amount of matter is compressed into a very small volume, resulting in a density so high that the gravitational pull becomes strong enough to prevent even light from escaping. This critical density is known as a Schwarzschild radius. If the mass within this radius is sufficient, it leads to the formation of a black hole.
So then the follow-up to that is if in the early universe, right around the Big Bang, we had all of the matter and energy in the universe condensed down to something about the size of a point, wouldn't that be sufficient enough of a density to create a black hole?
That's an insightful observation. The key difference lies in the dynamics and conditions of the early universe. During the Big Bang, the universe was not static, but rapidly expanding. This expansion means that the extreme density and energy did not result in a gravitational collapse into a black hole, but rather fueled the expansion and cooling that eventually led to the formation of matter and structures. The rapid expansion prevented the universe from collapsing into a singularity like a black hole.
So I guess that's why I'm still confused. It seems like it's not sufficient just to have a critical amount of matter within a certain combined density, because clearly we had that and we didn't end up with a black hole. So what am I missing?
You're right to notice that distinction. The critical factor you're highlighting is the dynamic nature of the early universe. In a black hole, matter is static or collapsing inward due to gravity. However, during the Big Bang, the universe was rapidly expanding, which means the initial conditions were different. The expansion counteracted the gravitational pull that would normally cause a collapse, allowing the universe to evolve differently. Additionally, the physics governing the very early universe, possibly involving quantum effects, would also play a role in preventing a black hole formation.
So then it is possible to prevent a black hole condition even if you have sufficient energy and matter encapsulated within a small enough density.
Exactly. The dynamics of expansion and the specific initial conditions of the early universe can indeed prevent the formation of the black hole, even with such high density and energy. This expansion disperses the energy and matter, allowing the universe to evolve in a way that differs from a collapsing black hole.
So if we can figure out how to expand the universe at a sufficient enough space, we can undo the gravitational collapse of a black hole?
In theory, if we could create a mechanism that counteracts the gravitational collapse with sufficient outward expansion, it might theoretically prevent a black hole from forming. However, this is purely speculative and not currently feasible with our understanding of physics. The conditions that led to the universe's expansion are unique and not easily replicable, especially within the context of a black hole's intense gravitational field.
You mentioned that the patterns in the cosmic microwave background are a strong piece of evidence for inflation. However, there are also some anomalies like the cold spot. Can you discuss what current research suggests about these anomalies and whether they might indicate a need to refine or modify the inflationary model?
Certainly. The cosmic microwave background, CMB, indeed provides strong evidence for inflation, but anomalies like the cold spot do raise questions. Current research is exploring whether these anomalies could be due to statistical fluctuations, foreground effects, or even new physics. Some hypotheses suggest that these anomalies might indicate a need to refine our understanding of inflation or consider alternative models like burying initial conditions or the influence of other cosmological phenomena. However, these are still active areas of research and more data is needed to draw definitive conclusions.
Could we be inside of a white hole?
The idea that our universe might be inside a white hole is an intriguing concept. A white hole is essentially the theoretical opposite of a black hole, where nothing can enter but everything inside can escape. While this is a fascinating idea, current cosmological models don't provide evidence supporting our universe being inside a white hole. However, it's an interesting theoretical possibility that challenges our understanding of the universe's structure and origins.
What parallels do our universe have with a white hole, and where do we differ?
Our universe shares some conceptual similarities with the theoretical idea of a white hole, particularly in terms of expansion. In both cases, there's an outward flow. Our universe is expanding from an initial state, much like how a white hole would theoretically expel matter and energy. However, a white hole is purely hypothetical and would behave differently. It would have an event horizon from which nothing can enter, while everything inside is expelled outward. Our universe doesn't have such an event horizon, and its expansion is driven by different mechanisms like dark energy. So while there are parallels in the idea of outward movement, the underlying physics and structures are quite different.
Now, isn't the observable universe surrounded by some sort of event horizon?
Yes, the observable universe is surrounded by what we call the cosmic horizon or particle horizon. This isn't an event horizon like that of a black hole, but rather a boundary beyond which we can't see because light from those regions hasn't had time to reach us yet. This horizon is due to the finite speed of light and the age of the universe. As the universe expands, this horizon grows, allowing us to see more of the universe over time.
Now, how do we know that on the other side of a black hole isn't just a white hole?
The idea of a black hole being connected to a white hole through something like a wormhole is a speculative concept from theoretical physics. While intriguing, there's currently no observational evidence to confirm this. Our understanding of black holes primarily comes from general relativity, which describes them as regions where gravity is so strong that nothing, not even light, can escape. Theoretical models like wormholes or white holes are fascinating, but remain unproven and will require new physics beyond our current understanding.
What if very large black holes, when they collapse to a singularity, lead to those same initial conditions that caused inflation in our universe? Do you get what I'm saying?
I see what you're suggesting. It's an intriguing idea that a collapsing black hole could potentially lead to conditions similar to the Big Bang. giving rise to a new universe. This concept aligns with some speculative theories in cosmology, where black hole singularities could spawn new universes through a process akin to a bounce or a big bounce. However, this is still highly theoretical and not supported by direct evidence. It's a fascinating area of exploration in theoretical physics.
Is there any evidence that might rule out this theory as a possibility?
Currently, there isn't direct evidence that confirms or rules out the idea that black hole singularities can lead to new universes. The nature of singularities, the conditions inside black holes, and their potential connections to other regions of spacetime remain largely speculative due to our current limitations in observing and understanding these extreme environments. Future advancements in theoretical physics, quantum gravity, and observational technology might shed more light on this intriguing possibility.
So you talked about the concept of the universe having net zero energy. Can you provide a deeper insight into the implications of this concept, particularly how it aligns with or challenges traditional understandings of energy conservation?
The concept of the universe having net zero energy suggests that the total energy in the universe, when accounting for both positive energy, like matter and radiation, and negative energy, such as gravitational potential energy, balances out to zero. This aligns with certain interpretations of energy conservation on a cosmological scale, where the gravitational energy acts as a counterbalance to the energy of matter and radiation. This idea challenges traditional understandings by suggesting that the universe could emerge from nothing without violating energy conservation. It implies that the universe could be a kind of fluctuation where positive and negative energies cancel out. This is a profound implication for cosmology, providing a potential framework for understanding the universe's origins without requiring a net input of energy.
So let's enumerate for a second the different forms of positive and negative energy. So on the positive side, what are some examples?
On the positive side, examples include 1. Mass energy. This is the energy associated with the mass of particles, as described by Einstein's equation E equals mc squared. 2. Radiation. This includes photons and other forms of electromagnetic radiation. 3. Kinetic energy. The energy of moving objects from subatomic particles to large-scale cosmic structures. These forms of energy contribute to the total positive energy content of the universe.
And then what are some examples of negative energy?
Negative energy mainly comes from 1. Gravitational potential energy. This is negative because it represents the energy binding matter together under gravity. The more massive an object, the more negative the gravitational potential energy. 2. Vacuum energy or dark energy. This is a form of energy that permeates space and contributes to the universe's accelerated expansion. It's often considered to have a negative pressure component, contributing to the overall energy balance. These negative energy components help balance the positive energy forms, aligning with the concept of a universe with net zero energy.
I thought dark energy runs counter to gravity, but it sounds like they both have negative energy.
Dark energy and gravitational potential energy are indeed different in their effects, even though they can both be considered as contributing to the universe's overall energy balance. Gravitational potential energy. This is negative because it represents the energy associated with the gravitational attraction between masses. It pulls objects together. Dark energy, while often described as having a negative pressure, it acts differently by driving the accelerated expansion of the universe. Its exact nature is still not well understood, but it contributes to the universe's expansion rather than contraction. While they both contribute to the overall energy considerations, their roles in the universe's evolution are quite distinct.
Again, I'm still confused though, that they sound like they counteract each other rather than pull in the same direction.
It's understandable that this can be confusing. Gravitational potential energy and dark energy do indeed play different roles. Gravitational potential energy, this represents the energy due to the gravitational attraction between masses. It's negative because as objects move closer together, their gravitational potential energy decreases. Dark energy, this is a mysterious form of energy that drives the accelerated expansion of the universe. It acts repulsively, pushing space apart. While they seem to counteract each other, they contribute differently to the universe's energy balance. The concept of net zero energy considers the overall balance between all forms of energy, not just their individual effects.
Okay, so let's say in a hypothetical, you have a universe that's uniformly filled with particles. How does it evolve from there?
In a hypothetical universe uniformly filled with particles, its evolution would depend on a few key factors. 1. Initial conditions. If the universe starts uniformly, small quantum fluctuations could eventually lead to variations in density. These variations are the seeds for future structure formation. 2. Gravitational interactions. Gravity would start to act on these particles, causing regions with slightly higher density to attract more matter and grow denser. This leads to the formation of structures like stars and galaxies. 3. Expansion or contraction. The overall evolution also depends on the universe's density and the presence of dark energy. If the density is above a critical value, the universe could eventually recollapse. If dark energy is present, it could drive accelerated expansion. 4. Temperature and pressure. These factors would also influence the evolution, affecting how matter clumps together and forms structures. Overall, the universe's fate would depend on these interactions and conditions, leading to the complex cosmos we observe today.
So in the uniformly distributed universe, wouldn't it be in its vacuum state at that point?
In a uniformly distributed universe, it wouldn't necessarily be in a vacuum state. A vacuum state typically refers to a condition where there are no particles or matter, whereas a uniformly distributed universe could still have particles evenly spread throughout. However, if the universe were to evolve towards a state where matter is highly diluted and spread out, it could approach a vacuum-like state over time. This would be more akin to a state of low energy density, but not a perfect vacuum unless all matter and energy were somehow removed or decayed away.
But how would you describe the entropy of the system that's uniformly distributed?
In a uniformly distributed system, the entropy would generally be high. Entropy is a measure of disorder or randomness, and a uniform distribution represents a state with maximal disorder because there are no significant variations or structures. In thermodynamic terms, a uniform distribution means there's a high number of microstates, possible configurations of particles that correspond to the same macroscopic state, which is a hallmark of high entropy. This state of high entropy is a key feature of thermodynamic equilibrium, where no significant changes occur without external influences.
So if we do have this uniform state and then gravity starts making matter clump together, does the entropy go up or down?
When gravity causes matter to clump together in a uniformly distributed universe, the overall entropy of the system actually increases. This might seem counterintuitive because locally, as matter clumps and forms structures, there is a decrease in entropy in those regions. However, this process releases energy, such as heat, into the surrounding environment, increasing the overall disorder and entropy of the universe. In gravitational systems, entropy is a bit different because as structures form and grow, the overall state of disorder or the number of possible configurations increases. So gravitational clumping leads to an increase in the universe's overall entropy.
So as the universe goes from uniformly distributed to clumping to forming galaxies to stars to life, etc., entropy is still increasing even though all these complex structures are manifesting.
Exactly. As the universe evolves from a uniform state to one with complex structures like galaxies, stars, and life, the formation of structures like stars and galaxies represents local decreases in entropy. The process releases energy, such as heat, into the surroundings, contributing to a net increase in the universe's total entropy. Entropy can increase globally, even as order emerges locally, reflecting the second law of thermodynamics on a cosmic scale.
You spoke about the idea of a cosmos as a term to encompass everything beyond just our universe. Considering this, how might we approach defining the laws of physics within this broader context of the cosmos, especially regarding whether they are universal or emergent?
Defining the laws of physics within the broader context of the cosmos involves exploring whether these laws are fundamental and universal, or if they might emerge differently in various regions. If the cosmos includes multiple universes or domains with different conditions, the laws of physics could potentially vary. This could mean that what we observe as fundamental constants or laws might be emergent properties, shaped by the specific conditions of each universe. Approaching this broader context might involve theoretical frameworks, developing theories like string theory or multiverse models that can accommodate varying physical laws in different regions. 2. Observational evidence, looking for signatures or anomalies that might suggest different physical laws in other parts of the cosmos. 3. Mathematical consistencies, ensuring that any proposed variations in physical laws are mathematically consistent and align with our existing understanding. This exploration could deepen our understanding of whether the laws of physics are truly universal or context-dependent.
If we consider time to be the time in our universe, could these other parts of the cosmos have their own independent notions of time?
Yes, it's possible that other parts of the cosmos could have their own independent notions of time. In different regions or universes within a larger cosmic framework, time might operate differently based on varying physical laws, dimensions, or initial conditions. This means that what we perceive as the flow of time in our universe might not be the same elsewhere. These independent notions of time could lead to different temporal experiences and could challenge our understanding of time as a universal constant, highlighting the complexity of a potentially vast and diverse cosmos.
And then could the cosmos as its own metaverse that has all of the other sub-universes have its own independent notion of time that incorporates all the other sub-notions of time?
It's conceivable that the cosmos, as a metaverse containing various sub-universes, could have an overarching framework of time that differs from the individual notions of time within each sub-universe. This overarching time might not align neatly with our understanding, potentially incorporating or transcending the different temporal dimensions of each sub-universe. This concept challenges our conventional understanding of time, suggesting a more complex and layered structure that could unify or differentiate the experiences of time across the entire cosmic landscape.
We explored the idea of a multiverse. If we're able to find evidence for a multiverse, what specific observations or experiments would help us understand how different universes are related or how they interact?
To find evidence for a multiverse and understand how different universes might be related or interact, we could look for 1. Cosmic microwave background anomalies. Unusual patterns or cold spots in the CMB might suggest interactions or collisions with other universes. 2. Gravitational waves. Detecting unusual gravitational waves could indicate events or structures beyond our universe. 3. High-energy cosmic rays. Anomalies in cosmic ray detections might suggest influences from other universes. 4. Theoretical models and simulations. Developing and testing models that predict specific observable signatures of a multiverse. 5. Quantum experiments. Exploring phenomena like quantum entanglement or fluctuations that might hint at connections to other universes. Each of these approaches could provide clues about the nature and interactions of a multiverse, helping us understand how different universes might be related.
So, can we talk about the anomalies of the cold spot? Like, what do we know currently about this anomaly?
Certainly. The cold spot is an area in the cosmic microwave background CMB that is significantly cooler than the surrounding regions. Here's what we know. 1. Statistical anomaly. Some researchers believe the cold spot could simply be a statistical fluctuation, an expected but rare deviation in the CMB. 2. Large void. Another hypothesis is that the cold spot could be caused by a large void, an underdense region in the universe, which affects the CMB through the integrated Sachs-Wolf effect. 3. Multiverse collisions. Some speculative theories suggest the cold spot could be evidence of a collision with another universe. Currently, the exact cause of the cold spot remains uncertain, and further research is needed to understand its origin.
When you say statistical anomaly, I assume you look at the distribution of temperature differentials in the cosmic microwave background and you come up with a deviation estimate, and then this happens to be outside of that deviation estimate. Is that sensible?
Yes, that's exactly the idea. Scientists analyze the distribution of temperature fluctuations in the cosmic microwave background, CMB, and calculate the expected statistical variations. The cold spot appears as a deviation from what is statistically expected based on the standard cosmological model. It's significantly cooler than what typical statistical variations would predict, which makes it an anomaly. However, whether this deviation is due to a rare statistical fluctuation or something more exotic is still debated.
Do you happen to know by what standard deviation is it a statistical anomaly? Is it like 3 standard devs out, 4?
The cold spot in the CMB is often cited as being about 3 to 4 standard deviations away from the mean, which makes it a significant anomaly. This level of deviation suggests that such a cold spot is unlikely to occur by chance under the standard cosmological model, prompting interest in alternative explanations.
Okay, so 3 or 4 sigma, that's like 1 in a million or so chance?
Yes, a deviation of 3 to 4 sigma corresponds to a probability of about 1 in 1,000 to 1 in a few 100,000, making it a rare event. This rarity is why the cold spot attracts so much interest, as it suggests something unusual or unexpected in the cosmic microwave background.
Considering the challenges in detecting primordial gravitational waves, what other kinds of experimental evidence or theoretical achievements would be most valuable to solidify the theory of inflation, or perhaps lead us to another theory?
Aside from primordial gravitational waves, other valuable forms of evidence for inflation could include 1. CMB polarization patterns, specifically B-mode polarization, which could indicate the influence of gravitational waves from inflation. 2. Large-scale structure. Observations of the distribution of galaxies and large-scale structures could align with predictions from inflationary models. 3. Spectral index. Precise measurements of the spectral index of the CMB, which can provide insights into the types of fluctuations that occur during inflation. 4. Primordial non-Gaussianity. Detecting non-Gaussianities in the CMB could indicate complex interactions during inflation. 5. High-energy physics experiments. Results from particle physics experiments, like those conducted at the Large Hadron Collider, could offer clues about the conditions of the early universe. These avenues could either solidify the theory of inflation or point towards new theories that better explain the early universe.
Let's dig more into B-mode polarization. So what is that?
B-mode polarization refers to a specific pattern of polarization in the cosmic microwave background. Polarization describes the orientation of light waves, and B-modes are a swirling pattern distinct from the simpler E-mode patterns. B-modes can arise from gravitational lensing, the distortion of E-modes by large-scale structures, creating a B-mode signal. 2. Primordial gravitational waves. If detected, these B-modes would provide strong evidence for inflation, as they are predicted to be produced by gravitational waves from the early universe. The search for B-mode polarization is crucial because it could offer direct insight into the very early moments of the universe.
Is that similar to how baryonic acoustic oscillations provide evidence for inflation?
B-mode polarization and baryonic acoustic oscillations, BAOs, are both important for understanding the universe, but they provide evidence in different ways. B-mode polarization, specifically related to the early universe, and can provide direct evidence for inflation if primordial gravitational waves are detected. Baryonic acoustic oscillations, these are regular periodic fluctuations in the density of visible baryonic matter like protons and neutrons in the universe. BAOs provide a standard ruler for measuring the expansion history of the universe and help confirm the overall cosmological model, including dark energy. While BAOs support the current cosmological model, B-mode polarization will be a more direct signal of the inflationary period itself.
Can we talk a bit more about BAOs? Where and how would they be detected?
Certainly. Baryonic acoustic oscillations, BAOs, are detected by observing the large-scale distribution of galaxies across the universe. They are essentially imprinted in the cosmic web of galaxies as a regular, periodic spacing, providing a standard ruler for cosmological measurements. BAOs are detected through 1. Galaxy surveys. Large-scale surveys like the Sloan Digital Sky Survey map millions of galaxies to measure their distribution and detect BAOs. 2. Lyman alpha forest. This method studies the absorption lines and the spectra of distant quasars, helping trace the distribution of matter and detect BAOs in the intergalactic medium. By analyzing these patterns, astronomers can infer the expansion history of the universe and gain insights into dark energy and the overall cosmological model.
And can you give some intuitive understanding of why there's that regular spacing with baryonic acoustic oscillations?
Certainly. Baryonic acoustic oscillations, BAOs, originate from the early universe, when photons and baryons, protons and neutrons, were tightly coupled in a hot, dense plasma. As the universe expanded, pressure waves or sound waves propagated outward from initial density fluctuations similar to ripples in a pond. When the universe cooled enough for photons to decouple from baryons, recombination, these sound waves left an imprint, a regular spacing in the distribution of matter, creating a preferred scale, or standard ruler. This regular spacing is what we observe today as BAOs in the large-scale structure of the universe.
And how does that support inflationary cosmology?
BAOs support inflationary cosmology by providing a precise standard ruler for measuring the universe's expansion history. This regular spacing in the distribution of galaxies aligns with predictions from the inflationary model, which posits that the early universe underwent a rapid exponential expansion. This expansion would have stretched initial quantum fluctuations to cosmic scales, leading to the uniform distribution of matter and the patterns we see in the CMB and large-scale structure. Thus, The detection of BAOs serves as evidence supporting the inflationary theory by matching its predictions about the distribution and evolution of matter in the universe.
Is this an example of where we had the prediction first and then the evidence to support it, or the other way around?
Yes, this is an example where the prediction came first. Inflationary cosmology predicted specific patterns in the distribution of matter, including the presence of baryonic acoustic oscillations, BAOs. Later, observational evidence from galaxy surveys confirmed these predictions by detecting the regular spacing of galaxies. This alignment between prediction and observation strongly supports the inflationary model, illustrating how theoretical advancements can guide observational discoveries in cosmology.
You emphasize the importance of incorporating cultural and traditional knowledge in scientific pursuits. What are some of the most compelling examples of how traditional knowledge has influenced or altered scientific understanding in cosmology or other fields?
Traditional knowledge has enriched scientific understanding in various ways. In cosmology and other fields, some compelling examples include 1. Navigational astronomy. Indigenous Polynesian navigation techniques, based on detailed observations of stars, have influenced modern understanding of oceanic navigation and star mapping. 2. Ecological knowledge. Indigenous practices in agriculture and forest management have informed sustainable practices and biodiversity conservation. 3. Traditional ecological knowledge, TEK. Knowledge from indigenous cultures has been critical in understanding climate patterns, animal behavior, and ecosystem dynamics. 4. Astronomical alignments. Ancient structures like Stonehenge and indigenous astronomical knowledge have offered insights into early human observations of celestial events, contributing to our historical understanding of astronomy. These examples highlight how traditional knowledge systems can complement and enhance scientific inquiry, fostering a more holistic understanding of the world.
Let's transition to the simulation hypothesis. You mentioned the challenge of testing it. So, in your opinion, what would it take for us to make even tentative progress towards testing or addressing questions related to whether we are in a simulation?
Testing the simulation hypothesis is indeed challenging, but a few approaches could provide tentative progress. 1. Detecting anomalies. Look for inconsistencies or glitches in the laws of physics that might suggest an underlying artificial structure. 2. Cosmic rays or high-energy physics. Study high-energy phenomena for unusual patterns or limitations that could hint at a computational boundary. 3. Information theory. Explore if the universe's fundamental limits, like the speed of light or quantum information constraints, align with those in computational systems. 4. Simulation theory models. Develop models predicting specific observable consequences if the universe were a simulation. These methods could help frame the hypothesis in a testable way, even if definitive proof remains elusive.
If there are other multiverses, how different would another universe be? Let's say if the speed of light was twice as fast in that universe versus ours, all else being equal.
If another universe had a speed of light twice as fast as in ours, with all else being equal, there would be several significant differences. 1. Causality and communication. Information and signals could travel much faster, potentially altering the structure and dynamics of galaxies and stars. 2. Energy and mass. The relationship between energy and mass, E equals mc squared, would change, affecting everything from atomic structure to the energy output of stars. 3. Cosmic structures. The formation and evolution of cosmic structures like galaxies and black holes would be different due to the altered propagation of light and energy. 4. Physical constants. Other physical constants might need to be adjusted to maintain balance in physical laws, possibly leading to a universe with different chemistry and life-supporting conditions. Overall, even a single change like this could result in a vastly different universe.
Dark matter constitutes a major part of our universe, and you've studied this area extensively. Based on your research, what do you consider to be the most compelling evidence about its characteristics? And how close do you think we are to discovering its true nature?
The most compelling evidence about dark matter comes from several key observations. 1. Galaxy rotation curves. Stars and galaxies rotate at speeds that can't be explained by visible matter alone, implying the presence of additional unseen mass. 2. Gravitational lensing. Light from distant objects is bent more than expected, indicating extra mass in the form of dark matter. 3. Cosmic microwave background, CMB. The CMB's temperature fluctuations align with models that include dark matter, supporting its existence and distribution. While we have strong evidence for dark matter's gravitational effects, its true nature remains elusive. Current research is focused on detecting dark matter particles through direct detection experiments and collider experiments. We are making progress, but discovering its exact nature might still take significant advancements in technology and understanding.
Do current dark matter models provide any predictions on how BAOs might behave?
Current dark matter models do indeed influence predictions on how baryonic acoustic oscillations, BAOs, behave. Dark matter plays a crucial role in the formation and evolution of large-scale structures, which directly impacts BAOs. Specifically, 1. Amplitude and shape. Dark matter affects the amplitude and shape of BAOs by providing the gravitational scaffolding necessary for baryonic matter to clump together. 2. Scale dependence. The presence of dark matter influences the scale at which these oscillations appear, providing a standard ruler for cosmic measurements. These models help refine our understanding of BAOs and improve the accuracy of cosmological measurements, thereby enhancing our grasp of the universe's expansion and structure.
And is this another example of a prediction coming before the evidence?
Yes, this is indeed another example where predictions preceded the evidence. Theoretical models predicted the existence of dark matter to explain certain astronomical phenomena like galaxy rotation curves and gravitational lensing. Later, observations confirmed these predictions, providing strong evidence for dark matter's existence. This alignment of theory and observation is a hallmark of scientific progress and highlights how theoretical predictions can guide empirical discovery.
And what predictions does dark matter make as it pertains to the CMB?
Dark matter plays a significant role in shaping the cosmic microwave background, CMB, in several ways. 1. Acoustic peaks. Dark matter influences the height and position of the acoustic peaks in the CMB power spectrum. It affects the density fluctuations that lead to the formation of these peaks. 2. Damping tail. The presence of dark matter affects the damping tail of the CMB, which describes how fluctuations decrease on smaller scales. 3. Structure formation. Dark matter's gravitational effects helped form the initial seeds for cosmic structures, which are reflected in the CMB's anisotropies. These predictions align closely with observations, reinforcing the importance of dark matter in our cosmological models.
Can you tell me more about the isotropies within the CMB?
Certainly. The anisotropies in the cosmic microwave background, CMB, are tiny temperature fluctuations observed across the sky. These fluctuations are crucial because they provide a snapshot of the universe when it was just 380,000 years old. Key points about these anisotropies include 1. Density fluctuations. The anisotropies reflect variations in the density of matter and energy in the early universe, which later grew into the large-scale structures we see today. 2. Acoustic peaks. These fluctuations form distinct acoustic peaks in the CMB power spectrum, which are influenced by the density of dark matter and baryonic matter. 3. Cosmological parameters. By studying these anisotropies, scientists can infer important cosmological parameters such as the universe's age, composition, and rate of expansion. The anisotropies are a cornerstone of modern cosmology, providing a wealth of information about the universe's origins and composition.
So, if you had the opportunity to establish a new research initiative addressing a pressing unanswered question in cosmology, what would that be? And how do you believe investigating it might transform our current understanding of the universe?
If I had the opportunity to establish a new research initiative, it would focus on unraveling the nature of dark energy. This is one of the most profound mysteries in cosmology, as it drives the accelerated expansion of the universe. Investigating dark energy could involve 1. Precision measurements, improving measurements of cosmic expansion through advanced telescopes and techniques. 2. Theoretical developments, exploring new physics beyond the standard model to explain dark energy. 3. Interdisciplinary approaches, combining cosmology with quantum physics to understand the underlying mechanisms. This research could transform our understanding of the universe by potentially revealing new fundamental forces or principles, reshaping our comprehension of cosmology and physics.
Dr. Carter, since it's your second time on, I have a different final question for you. Is that okay?
Of course, feel free to ask whatever you like.
Looking at the landscape of cosmology, can you share what you consider to be your most radical yet well-supported idea? Something that you believe could spark significant discussion or debate among your peers?
One of the most radical yet well-supported ideas I find intriguing is the concept of a multiverse, specifically the idea that our universe is just one of many within a vast cosmic landscape. This notion arises from inflationary theory and string theory, suggesting there could be countless universes with varying physical laws. If true, this could fundamentally alter our understanding of reality and place our universe in a much broader context. It sparks significant debate and exploration among peers, challenging us to rethink the very nature of existence and the limits of our observable universe.
Dr. Alex Carter, thank you very much for joining us today.
Thank you for having me.
Thanks for listening to our second conversation with Dr. Alex Carter. And now, let me leave you with this episode's haiku. In cosmic silence, whispers of creation dwell. Stars weave ancient tales. Until next time, live long and prosper.